Hello, welcome to the fourth lecture. So now we are going to discuss a different code that is based on everything we explained before. But this builds the intensity profiles of accretion disks with taking into account the inclination of an observation angle from the detector. And also we add some structure to the disk. And so the accretion disk will be will have some structure, some rotation. So let me share the notebook, and then I explain also the structure of the notebook. This is designed to make it more adaptable in such a way that I have separated many functions so that the modular structure of the code is more transparent. Okay, so you can make alterations or modify some functions without affecting the others. So I think it's more versatile. And so this is it. Let me quit the kernel because I was playing with it just before. And now to start, we define the geometric part. Okay, the metric. Basically, I'm defining the metric through this command get g. G is the metric. We are working with axially symmetric spacetimes. Okay, the general family that I introduced before in the previous lectures. And it is of the curve-like form, but because they have this parameter A that is associated with the rotation, but I have added also this Rm squared parameter that generates black bounces. Okay, so this particular line element corresponds to a curve-like black bounce. Okay, so we can play with these parameters, with the mass, with the angular momentum of the black hole, and with the size of the wormhole throat, depending on the parameters. But the internal structure, the minimum of the area functions. Okay, so the line element is defined here. No mystery, nothing special. This function, this module. Okay. And then the inverse metric is obtained simply with this command, get G inverse. Okay, compute the inverse of get G. Okay, that's it. So we execute this, and that's it. And now we set up the Hamiltonian equations. And this is basically the same module as before. The mass, the energy, and we need to add the parameters of the new model. So we have the Rm parameter and the rotation parameter. Okay, so we define the momentum vector in local variables, the Hamiltonian, remember, pi, the inverse metric times pi divided 2. This is the Hamiltonian. And then the Hamiltonian equations are written in the same way. The partial derivatives for the spatial variables and minus the partial derivatives for the momenta. And then we define these functional expressions. We turn them into numerical expressions, okay, to speed up the numerical integration, right? To make mathematical deal with numbers and not with functional expressions. Okay, so it's written in this way. It's a small modification of the previous code, but then this is a way you can compare. Okay, very good. So these are the equations. And now we define, like before, the integrator of one geodesic. Yeah? The integrator of one geodesic has exactly the same logic as before. We need simply that this and the integrator now is called only with this input, the initial conditions for the equations. Everything else will be provided in a more efficient way. So the equations are simply the derivative of the variables. Okay, the variables is this set of variables, you know. Okay, the positions and the momenta, and those derivatives are equal to the numerical values of the functional expressions for these quantities in the chosen background metric. The initial conditions, the same way, are defined the same way as before. When lambda is 0, we take this input data that comes from here. And then the maximum affine parameter is set to 2.5, but it could be 2 or even less, okay? Cut points row is the same as before, an empty set where we will store the information of the intersection of the geodesics with the accretion disk. And then we carry out the numerical integration. And the structure is basically the same. We have the ND-solve solver, the equations, the initial conditions, the condition to stop if we get very close to the center. Now we are dealing with a black bounce metric, so we don't really need to get to R0 because there is a minimum. But anyway, this R can be seen as the coordinate. So we will, I mean, this is not really important because I'm going to focus on the black hole scenario. So we only care about the external geodesics. If we were to study black bounces, I don't really know if this condition, maybe we need to adapt this condition to deal with the wormhole. But for the examples, the illustration that I'm going to provide here, this is irrelevant. And now the condition for intersection with the accretion disk is this one, okay? Theta now is the polar angle. Remember, in the previous lecture, I was changing the variables, but now we are working with the correct variable. So the equatorial plane is at theta equal to pi over 2, okay? So whenever the cosinus of theta is 0, this is pi over 2 or 3 minus pi over 2 or pi over 3 pi halves. Then in all those cases, the cosinus is 0, and then we have intersections with the accretion disk. So we store data, okay? The cut points row that was initially empty now is filled with some information. The point, and here I'm basically saving all the information, okay? Not just the radius, okay? For a given impact parameter. We are saving the radius, the angles, and also the momentum, okay? When I was explaining the theory, I mentioned that if we want to compute the Doppler shift, besides knowing where the photon hits the disk, or the geodesic hits the disk to get a photon, we also need the momentum in order to be able to compute the Doppler effect, because the particles of the fluid will have some motion, either circular or in falling, okay? So it is important to save the value of the momentum of the photon when it hits the accretion disk. Okay, so we are saving all this information in cut point row. Okay, and now we don't really care about the order of the intersection. If we're intersecting once, twice, 3 times, or more, we don't really care. Okay, that was useful before to learn a little bit how the final intensity profile, the final picture was built out of the translation of the initial of the emission profile to the detector through the different mechanisms. Okay, now we don't really care about that, so we just store intersection points. Okay, and we don't care about labeling them as the first, second, or third, or higher. This code doesn't care about that, okay? Because we want an inclined perspective, so that is completely irrelevant to know if the intersection is 1, 2, or not. Okay, the other parts of the code are standard, the same as before. And now, once we have integrated the equation, we have the post-integration manipulation of the data. Okay, and we will assume that the disk has axial symmetry, okay? Why this? Well, this is simply a simplification, okay? But we don't really need to do that. But I'm doing it anyway here. So, and what this means is that I will not store the angular parts. If for some reason we were to define a disk that is anisotropic, okay, on the plane, if the intensity distribution depends on the angle, okay, then we should keep the information about phi, okay. If it has some thickness, then we would need also the information about theta. But now I'm simplifying that, okay. So I will only keep the radial location and the momentum, okay. The radial location because it's necessary for the gravitational redshift, and the momentum because together with the radial position, it is necessary for the Doppler effect, okay? So this is what we do. We take the cut points raw, this data, and manipulate them simply to get the radial position and the spatial momentum, okay? We had the position was a vector, this first vector, and the momentum was this other 3 vector, okay? What we are doing now is to define the radial impact position, which is the position, the first component of this vector, which is r, and then we build the covariant momentum vector as this 4 momentum, this 4 vector, okay? The first component is minus energy, and the 3 other components is this vector here. Okay, nothing special, but we need this 4 vector to compute the Doppler effect, okay, to make the scalar product of the velocity vector of the fluid with the momentum of the photon. Okay, and that's it. So we are saving now the data like this, okay, in this function local cut points. Okay. So this integration and the integrator now is giving us output these local cut points, which are these 2 informations, the location of the impact and the vector. We are not plotting any geodesics, okay? And we are not keeping track of the order of the intersections, okay? We are just storing data about intersection and momentum, okay? Because we already know how everything else works. Okay? We did that in the previous lecture. Okay, so this is the integrator for one geodesic, and now we need to integrate many geodesics. Okay, so this is the part that is more different from the previous code, because here I decided to split the different elements of the iterator. On one side, I defined the square grid, the detector, the grid of pixels. I choose simply a square grid. And so I define and this is defined by a range of, let's say, impact parameters and the number of geodesics. This is the number of subdivisions of each axis. The x-axis is divided in ng elements, and the vertical axis in ng elements. So the number of geodesics actually is ng squared. Okay, so we have ng squared pixels for our image. Okay, and what we do simply is to define the step, the step between pixels, and we build a table with alpha beta, so that alpha goes from minus range to plus range in a number of steps, okay? And the same for beta. So it's a rectangular array, Cartesian array with pixels, okay? This is just a choice of grid, okay? Maybe there are better distribution of pixels on a given grid, okay? It's not necessary to use a rectangular grid. There are other forms of distribution that optimize the space between points. So you just need to, if you want to change the grid, simply modify this. Okay, so this module, you change it and you explore with other grid distributions. Now, once we have defined the grid, we need initial conditions for each point on that grid. So I define this new module to compute the initial conditions for each grid point. Okay, so again, as before, I define the distance to the detector as 100 units. The inclination angle, now I'm assuming that 100 is very far away. So I'm not considering this is an approximation. If we define the direction, we can improve this, but I'm not very interested on that. So this will be the same information for all rays, okay, as I explained in the second lecture. And well, it's not difficult to improve this, but I'm not going to do it. You just can take like 3 here, and then any error made here in this approximation is corrected by the distance here. Okay, but to simplify things and make the code faster, I just put 100, and if we have to write a paper, then we do things correctly, okay, with more precision, more points, a better refinement. Now we are just playing. This is a proof of concept, and that is what really matters. We don't want to spend here hours doing the calculation. So we have this initial data for all the spatial part of the grid points, and now we need the momenta, okay? And since we have the grid in terms of alpha and beta, we build the azimuthal angular momentum, LC, for each alpha and for the chosen inclination, okay? And also we compute the Q, the Carter constant, for this value of beta, alpha, and for the parameters of the black hole. Since this is a rotating black hole, we have to include this part, okay? This was already explained in the second lecture. And so we have this initial condition for the azimuthal momentum. For the theta, the polar momentum, we have, remember this square root, okay? And we have to add the sign of beta. This is important, okay? Because beta can be positive or negative, okay? So in order to encode that in the theta momentum, we have to put it here, okay, explicitly. And then to compute the radial momentum, we need to use the Hamiltonian constraint. And for that, we need to compute the inverse metric. Okay, so this is why we do that. We compute the inverse metric and then use the square root of the corresponding Hamiltonian constraint. So this is simple. We did that by hand in the lecture where we explained the theory. Okay, and so finally, for each grid point, we have these initial conditions. The spatial sector is the same, and the momenta depend on the pixel that we choose, okay? And note that for the radial momentum, we are taking the minus sign because we are integrating backwards, okay? From the detector to the accretion disk. Okay, so and we do that for all the elements on the grid, okay? Very. And that's it. So this computes all the initial conditions. So we have the grid, we have the initial conditions for that grid, and now we only need to take to iterate the integration of one geodesic for all these for all the points of this grid. Okay, so we need to give the grid and the initial conditions for that grid. Okay, so then we set the equations for chosen values of the mass, of the energy, and the parameters of the metric. We use this to define the global functions because since these are very intensive calculations, okay, because we have ng squared pixels, so there will be many calculations and they can be parallelized, okay? So this, in the previous code, I was using a table to do the calculations because we only needed one line and then rotate the results corresponding to that line. Now we have to integrate geodesics on all the plane, okay? So it is better to parallelize the calculations, exploiting all the resources of the cores of the computer, okay? So this command takes care of that. And this is useful in order to share the right information with the different cores of the computer, okay? But the application is simple. We just need to give to each individual integrator the initial data, and we have to run over all the initial data of our grid, okay? That's it. No more difficulties. Okay, it's very simple. Now we have separated all the elements. So before the ray tracer was a big module. Now it's very simple because we have taken outside the definition of the initial data and the definition of the grid. Okay. This is also useful if you want to consider different kinds of black holes. If you don't have spherical symmetry, for instance, if you consider a multi-center distribution of black holes, of extremal black holes, and you want to study, I don't know, the propagation of light rays in that spacetime, you don't need to use spherical coordinates and those things, and you can the logic of presented here is still valid. Okay, so it's very adaptable. Okay, so now that we have all the code for the integration, we don't really need much more. It's very simple. We just define the properties of the disk. Okay, this is the intensity profile, the same functions as we did in the previous lecture, the same examples. Okay, and now and now what we need to do is to care about the propagation of the intensity profile. Okay, so we have computed the geodesics, the previous part of the code. We are defining the intensity profile, which is isotropic on the equatorial plane. Okay, isotropic because it only depends on the radial position. There is no angular dependence. If there were angular dependence, then remember we would have to store more information about the angular position of the light rays when they reach the disk. Okay, but it's not our case. And now what we need to do is to give some dynamics to this disk. Okay, this is the intensity profile, but now we can give some velocities. Okay, and for the velocity profile, well, we introduce the velocity profile through the redshift function. Okay, so we will compute the redshift for each geodesic using this information. Okay, the position where the geodesic hits the disk and the momentum of the photon in that position. Okay, now this other variable R ISCO represents the location of the ISCO of the particular model we are considering. Okay, and this is so because I'm going to split the disk or the equatorial plane in two sectors. Okay, specific for these Kerr-like solutions. For radii which are larger than the ISCO, then I will assume that the disk is rotating in circular stable orbits. So it's Keplerian. So it's simply rotating with some angular velocity that is determined by the theory. Okay, and that angular velocity omega is given by this expression that one can obtain in the Kerr-like metrics. The different quantities here involve derivatives of the components of the metric. So these are Christoffel connections of the metric. I'm computing those derivatives numerically. Know that this is R plus epsilon, R minus epsilon divided 2 epsilon. Okay, so this is a numerical derivatives because it's faster than encoding the formal expressions. Okay, evaluating formal expressions takes much more time. Okay, and since we are computing hundreds and thousands of geodesics, any additional calculation will slow down your code. So and we don't want that. So we prefer numerical evaluation of quantities than evaluation of expressions, of functional expressions. Because Mathematica can do it, but takes much longer. Okay, so this is what we are doing. If the radius, if the location of the point that we are studying is beyond the ISCO, then we consider Keplerian orbits. Okay, and if the radius is below the ISCO, then we assume that the gas is being accreted radially towards the black hole. Okay, and in that case, the velocity vector is given by this expression. Okay, it has the time component and the radial component. because there is only radial motion. In the previous case, we had the time component and the angular motion, because we didn't have radial motion because these orbits beyond the disco, we have circular orbits. So the radial component is not changing. Okay. And that's it. This is our redshift function. So for now we will see how it works. Okay, let me evaluate this. Okay. And if you want to design a more involved profile, you are invited to modify or improve this function. Okay, this module. So this is why I'm separating things in modules. Okay, just to make it more adaptable and easier to modify. Now the intensity profiles. So how do we compute the intensity profiles? Okay, once we have all the information about the geodesics and the intersection points with the accretion disk, we can build the intensity map. Okay. So we need to provide the data of the rays. The data rays here is given by, where are the data rays? Yes, these are on the data. Let me see what this means. So we need the alpha and beta, the positions of the grid, the information of the impact. This is P3 contains the radius and the momentum, okay, the force momentum. And this must be here in data rays, okay? So we compute for every element in the data rays. Well, yes, exactly. This data rays is this function that we have here, rays info. Right? Rays info, remember, it contains yes, it must contain the alpha beta, so the pixel, and then for each pixel, the intersection points for that geodesic. Okay, because each pixel may have contributions from different intersection points. Okay, and each intersection point contains the radius and the force momentum. Okay, remember that. Okay, so now we compute intensity map in this way. We compute the redshift function that is given by the radial position, the K, and yes, and the ISCO. So the radial information is in this function, impacts. These are the impacts. Let me see, impacts is P3. This is the first component of the vector P, the second and the third. And where is this P? Ah, yes, P is data rays. And this data rays was the rays info, okay? Yes, exactly. Yes, the rays info, because in rays info, the first component was alpha, the second was beta, and the third was R and the force momentum, okay? So this P3 must have two components, I believe, or the impacts must be somewhere. Yeah, anyway. So this is the point, that G is the, yes. So this, yes, get redshift is R and K. So R and K are here. These imp are the impacts, and these impacts comes from where? Impact is P3, exactly. So P3, as I said, contains the information of R and K. Okay, the first entry for each imp is the radius, and the second entry for each imp in the set of impacts is the force momentum. Okay, now it's clear. And remember, the redshift function, get redshift, gives us output this quantity minus the energy divided the force velocity of the emitting particle multiplied by the covariant, the force momentum of the photon in that location. Okay, so this gives the factor G that contains the gravitational redshift and the information about the motion of the fluid particle, and we compute the G4 in that location. okay? So the total intensity that we observe is precisely G4 times the emitted intensity profile, okay? And we need to specify which intensity profile we are considering, okay? And also the location of the ISCO, okay? Good. Depending on the model, you may need a function, an independent function to compute the location of the ISCO, okay? I don't remember if I am putting here correctly the definition of the ISCO, but it should be correct for the non-rotating case. But I'm not sure if it is really correct for any Kerr black bounce, okay? But this is a minimal incompleteness of the code, okay? It works, and I'm just warning you about that because I don't remember exactly. I remember I had some difficulties encoding the ISCO, and I know I had to make a specific function to compute the ISCO for different models. But I think that here is for this kind of metrics, it is correct, okay? And if it is not, then I'm just warning you about that, okay? Very good. So this is how we compute the intensity profile, okay? Once we have all the race info, okay, we choose an intensity profile, we specify the location of the ISCO, and then this quantity computes the redshift factors and modulates the emission profile with those redshift functions, factors. And that's how we obtain the total intensity for each pixel, alpha beta, okay? Very good. So this is short, but it's condensed. It's condensing a lot of information. Okay, very good. So there we go. And now that's it. We have all the theory here. Now we just need to compute some example, okay? And as an example, which is up below, I'm going to consider this case, a Schwarzschild black hole. So it's not a black bounce because the parameter of the black bounce is 0. It is non-rotating, okay? We set the mass of the black hole to unity and the energy of photons to unity, okay? The standard parameterization. And we are making these variables global, okay? In the previous lecture, M and En energy were local, okay? But that's a complication. When we have so many module functions, it is better to make these parameters global so that the parallel computation doesn't miss information and we minimize risks. Okay, so as I said, the location of the ISCO, we are giving it like this. So there is no dependence on the A parameter of Kerr. So probably this is not valid for Kerr, okay? But anyway, it's a minimal detail. So now I choose, this is my model, which is basically Schwarzschild, okay? And I'm going to compute the grid. I first compute the grid for a range of 12 units from alpha 12 to alpha minus 12, and the same for beta, okay? So it's a range sufficiently big. It's like 24 units of impact parameters, 12 on each side. And I'm going to divide each axis in 50 elements. So we will have 50 times 50. This is 2,500 geodesics, okay? The number of geodesics is geodesics or pixels, right? And this takes 1 minute to compute, okay? And we will show that. Also, so we define this grid with these characteristics, okay? From plus 12 to minus 12 with 50 elements in between. And the initial conditions are computed for this grid and this inclination angle, okay? In the previous lecture, we were looking at the black hole from the North Pole, okay? That was theta equal to 0, okay? Now we are looking at the black hole with the detector near the equatorial plane. So from 80 degrees, almost 90. If it were 90, it would be on the equatorial plane, but it is a bit inclined with respect to the 10 degrees of inclination respected to the equatorial plane. So the perspective is more like the one you see in the interstellar movie, okay? Very good. So this is just the computation of the grid and the initial conditions, and automatically we call the iterative computer module that computes the geodesics for that grid and those initial conditions. So this is automatically launching the parallel calculations, because remember we use the parallel table, right? It was here. This is the command that's parallel table, parallelizes the calculations. So as you can see here, it is computing 45 items on each of my 8 kernels. So if your computer has more kernels, it will be faster, okay? So as I said, this I'm just using 50 geodesics, well, 2500 geodesics as a proof of concept. So probably this picture is going to have very low resolution, but I'm not going to spend here 40 minutes getting a high resolution image because the lecture is finite. Okay, so it is not going too slow, just 1 minute. It is taking like 1 more minute to complete this. And we are here. So maybe we need to update this. This is 2 minutes. This is 2 minutes. I don't know why before it was only 1 minute. Yeah, probably because I was not recording, okay? Because since I'm recording the call, so I have the Zoom open, that is consuming some resources in my computer. So only using Mathematica, it takes 1 minute. With other services running, then we have to share resources and it slows down, okay? So I did well computing all these examples in advance. So I'm just showing you this explicitly, and the others, I will show you the results that I obtained when I was alone without the Zoom working. Okay, so it's time to check your Instagram or your email or send a WhatsApp to your family and friends. Yes. We just need to wait a little bit, but only 50 more seconds. So it will be like 3 minutes to be fair. 3 minutes. And we will see a disappointing picture of a black hole with very low resolution. Well, disappointing because of the lack of resolution, okay? But I'm very satisfied with the result because this simple code is able to compute the intensity profile of these things. Yeah, I would like to invite you to read the paper by Luminet when he did the calculation of the first shadow of a black hole, and he did the calculations and the drawing by hand, okay? So go there because probably it took him more than 3 minutes to get that plot. Okay, so now we have computed all the geodesics, okay, all the intersection points. We have the race info file. Array is the one that we want. Let me check the length of that array, race info. As I said, to 2500, 50 times 50. And now what I have to do is to convolute the intensity profile that we chose. In this case, we are using the third intensity profile. You will know which this is the ISCO one, the one picked at the ISCO. Okay, it's the blue one is the third intensity profile 3. And we need to generate this intensity map. And then we can plot it with this density plot. And this is what we get. As I said, this is quite disappointing. Oops, I'm frozen. I'm frozen. I'm no longer frozen. Okay, so this is the disappointing picture that we get. So is this just a lack of resolution? No, not really. what we have here is a problem of contrast, okay? And the problem of contrast is that is because the intensity of the maximum intensity in some regions is orders of magnitude larger than in other regions, okay? So this is what doesn't allow us to see well the structure of what's going on, okay? And that's the reason why I'm using here, besides the basic intensity map, okay, I'm also going to compute the logarithm of the intensity profile, okay? I'm going to represent this same plot in alpha and beta, okay? These are the alpha is here, beta is the vertical, okay? But instead of representing the raw intensity, I'm going to represent the logarithm of the raw intensity plus a minimal addition, just to guarantee that there is not zero, anything that is zero, okay? We just add this minimum. This is already computed, and if we evaluate this, the density plot, in this case, let me see if it shows up. It's here. I don't know why it's not. Okay. Now the same data, the same set of data in logarithmic scale is now showing more clearly the structure of the intensity profile. Okay. This really looks like a black hole with an accretion disk, right? And know the different elements. Okay. So we have the direct image, that is this disk. Okay. In particular, this one. This is the direct image. This is coming directly to us. Okay. This is the upper part of the accretion disk that lies behind the black hole, but this is deflected and is coming us from the backside of black hole. So these are the light rays from the backside of the black hole that are emitted upwards. Then they are deflected and are able to reach us. Okay, and this lower part corresponds to the light rays that are emitted from the backside, the lower part of the accretion disk, downwards. Okay, then that they are deflected and they come towards the detector. Okay, so this is the lensed image. This is lensed, this is lensed, and this is direct. Okay, and then here we can see some points that represent the photon sphere. Okay, remember that in our case, in the previous lecture, we were able to see that in this same intensity profile, that was a very thin ring of light that represented 0.17% of the total intensity. Okay, so it's very dim. So here we see something, okay, but the global picture is what we expected. Okay, now there is something else. Note that there is yellow here, and it's very red here. So why is that? This is a Doppler effect, because the disk is rotating like this, from left to right. So when the gas particles are coming towards us, then the photons gain momentum, gain frequency, okay? And then they look brighter. Now this is why this side of the accretion disk looks brighter, okay? This is an effect that was not present in the previous code, in the one that we were looking at the accretion disk from the North Pole, okay, that everything was isotropic on the equatorial plane, okay, because we were not implementing any velocity, and also from the North Pole, probably you can't see anything. But from this perspective, you do see the brighter side and the cooler side, okay, or darker side. Okay, so this is basically what we wanted. Now we can just improve the picture for a Schwarzschild, increasing the number of points. Okay, now we were dealing with 50 geodesics. Now let's see what happens if we increase this to 50 geodesics. No, 50 subdivisions of each axis. Now, if we double this, then we will get a factor 4 here. So we will have 10,000 geodesics. Okay. So I'm not going to do that because it takes much longer than 4 minutes. Okay, when Zoom is not working. It takes 4 minutes, but now probably takes 12 or 20 minutes. And this is what we get. Okay. And this is what happens when we increase from 50 to 100. This is with 10,000 geodesics. Now the photosphere, this light ring, is more visible. We have increased the number of geodesics that intersect in that point, but it's not completely clean. And it's not clean in part because we are using a rectangular array. Okay. If we had chosen an array with the points distributed in circumferences or ellipses, probably we would be able to touch more points of this circumference with the same number of pixels. Okay, so and actually we don't really need so many pixels on this part. So we could remove pixels from here that do not contribute to the intensity to speed up the calculation and increase the number of pixels over here. So this is something that we can do now by manipulating the grid function. Okay, when we define the grid here, get redshift, where is the grid? Yeah, the grid was here. Here we define a square grid, but we have freedom to choose the distribution of points. So if we find clever ways, more clever ways to distribute our pixels, it is likely that we can speed up the process and get much more resolution with the same resources or with less resources. Okay, so it's just a matter of being clever and improving some parts of the code. Okay, I leave that for you so you can play. You have more time. You are more intelligent than me. I'm just an amateur player of numerical codes. And that's it. So this is what happens, how it improves with 100 geodesics. Okay, and if we add 300 times 300, this is 90,000 geodesics. Then the picture, this one is much better. But the one that the logarithmic representation is now wonderful. Now this is smooth, the light ring, you can see, okay, we have gained a lot of accuracy. So this is something that you can put in a paper, okay? This is a plot that is worth using in a publication. Okay, we have 90,000 geodesics pixels, and now the profile of the Doppler blue shift and the red shift is clear from this, both in the direct image and in the lensed image. Okay, the light ring is there. We have many data, and that's it. Okay, so this is for the Schwarzschild black hole. And now, just as an illustration, let me consider a Kerr metric. Okay, so we don't need to close the kernel. Simply clear the data and introduce a non-zero angular parameter for the Kerr metric. Okay, so I'm not going to execute it because it takes longer. Okay, because in the Kerr metric we have more elements in the metric, so that means more calculations. So if for Schwarzschild with 100 ng it takes 4 minutes, for Kerr it takes 7 minutes. Okay, and what we get is the following. This is the, oops, I don't know what happens. Okay, yeah, we are back. Okay, this is what we get. We have some deformation, in particular the light ring now is no longer a circumference, but it's more like a D. So it's actually a D is flattened from this side, the circumference. Okay. The accretion disk is still rotating in the same way towards the right, but note that the lensed image from below is deformed due to the rotation, okay? And this is taking the A parameter to be 0.5. So what happens if we change the sign? If we take A equal to minus 0.5. So what happens is the following, is this. That the deformation is from this side, The D now is the circumference now does look like a D, as it should be. But since we have not changed the accretion disk is still rotating from left to right. Okay, this is why the blue shift is on this side. Okay, but we get some deformation here. Okay, so this is a combination of the rotation of the black hole that is opposite to the rotation of the accretion disk. Okay, so there are all these deformations contain information about the properties of the background. So this code, even if it is simple and we are just playing with 10,000 geodesics, it shows the capabilities that it has to extract physical information from the intensity profiles. Okay, when we have some inclination, when the observation angle is not from the North Pole, we have access to other other sources of information about the rotation properties of the black hole and of the gas. Okay, so that's it. This is what I wanted to show you. I have explained the basic theory that leaves open some questions if you want to go beyond Maxwell electrodynamics. Those aspects affect the propagation equation of photons, the conservation laws. Conservation laws are very important. And well, you have two different codes to analyze the intensity profiles. One for north, when we look observation from the North Pole, okay? And this one that provides the observation from any other inclination angle. And this choice of two codes is not arbitrary, okay? It is because this particular code with inclination angle doesn't work when the inclination angle is 0, okay? Remember that. Because of the choice of coordinates that we did. For the initial conditions, let me see where are the initial conditions. The initial conditions are here, okay? When theta is 0, we cannot divide. I mean, the angular momentum for any alpha will be 0. Okay, so this is a limiting case. If you can put, if you want to explore the almost 90 degrees perspective, just put a number that is like 89 or I mean 0 or 1 degree. Not so yeah. If you want to look at the accretion disk from the North Pole, I recommend you to use the other codes. Okay, but you can still use this one, putting a small angle here, but never 0, because with 0 it crashes. Okay, and it is better to use the other that is faster and has more resolution. And this is better if you want to explore from some different angles. Okay, so they are complementary in that sense. And that's all I wanted to explain. I hope that you find these codes interesting and the theory. And if you have any questions, feel free to contact me. I want to make these codes available in some way very soon. So since the videos will be available on the website of this Amazonian workshop, I will give you instructions or directions on how to get the code once I make them available online. Okay. Thank you so much and enjoy the rest of the conference. Bye bye.